interference as well as. So let's continue from that point onwards. So since few students are yet to join in, let's start with a revision question of interference of waves in the meanwhile.
Good morning, sir.
Good morning. Good morning. We had seen for interference, if we have two waves traveling in the same direction and of identical frequency, then their superposition or overlap results in interference, which gives us some net amplitude which depends on the phase difference. And to calculate the net amplitude, we can either draw a phasor diagram or directly write the formula related to the phasor addition.
So that's epsilon, right?
Yes. We can represent it by any simple alpha, beta, epsilon. Just
Okay.
I have chosen. Okay. So let me go over here. The important thing is the value of that is this phase angle here, and the value of the net amplitude is this. Okay. So we have the formula. And that phase angle is so. Let us look at a couple of examples of this today. Okay. Now we had also seen here that the phase difference phi can be due to a path difference, so delta x, and or time difference, delta t. So phase difference that is created because of path difference is given by 2 pi by lambda into delta x, and phase difference that is created because of time difference so we had seen a couple of problems based on this, so we'll see another example later, but right now let's do an example like this. Find the resultant amplitude from the superposition of y1 and y2. We just try this out, people. We'll discuss. So you can just express the cos term in terms of sine by using this formula that sine of x plus pi by 2 is cos x. So this can also be expressed as Viraj, let's check out the answer. Yes, it's correct, your answer. Or you can also solve it this way that
So 2 root.
Okay, so those who have joined late, just and minimize so you can note down this question, work it out later. We're just doing a quick recap of interference. Even though after interference, we've also done standing waves in the last lecture. This is the most important part of this chapter, so I'm just doing some additional practice questions. Okay, let's do another example. So this time what we have here is spring going to infinity, which is under a tension of 100 newtons and has a linear mass density so much. Okay. Now there are three sources, S1, S2 and S3, which are equidistant from each other. So S1, S2 and S3 are simple harmonic oscillators with equal amplitudes along y-axis, identical frequency, Hz each. Okay. And are simultaneously started at t equal to 0 in synchronization. So if this distance d is 1/6 of a meter, that is approximately 'then find the net amplitude due to their superposition at the point P. So this is like a situation of three-wave interference. Okay. So your best advice to use the Phasor diagram method rather than algebraically to solve it. But first of all, you have to understand the phase difference between the three waves, because while the three sources S1, S2, and S3 are in sync, but they are not at the same position. So the waves traveling from S1, S2, and S3 to the point P will have some phase differences because of path difference. So this is an important concept to be able to apply over here. Yes, Parth, I will just verify your answer. It's correct. Very good. So the first thing we have to understand is from the given tension in the thread and the linear mass density, which we will write as this much in SI unit, we will see that the propagation speed will become 50 meters per second. And the frequency is given 50 hertz. Okay, so the wavelength will become 1 meter. Just a minute, people. Right. So next thing, the wavelength you got. Now you can see that if we consider this point as x equal to 0, okay, or whatever, you can consider it x naught also. This is x equal to d. This is x equal to 2d. So, and this is x equal to x, suppose. So the wave that is coming from the first source is omega t minus kx, suppose. The wave coming from the second source is omega t minus k x minus d. So you can write that as a naught sine omega t minus kx plus phi 1, suppose, okay, where phi 1 is kd or 2 pi by lambda into d. And similarly, the third one is like this. Okay. Now we use the value of d which is given. And lambda we just saw is 1 meter. So phi 1 comes out to be
Pi by. So that was 1 by.
1 by 6. Yeah. Yeah, it will come out to be pi by 3. Correct. So now when we are doing the phasor addition of these waves, we can just use a phasor diagram. We can do this manually also, but it just be very lengthy comparison. Okay, so now this phasor addition we can just do by drawing a simple phasor diagram like this. It will be much easier, they said. So the first amplitude, if we represent like this, the second one is at 60 degrees to this, let's say like this, and the third one is at 120 degrees in comparison. So you will recall from all that practice of vector algebra that you have done. So that these are the three consecutive sides of a regular hexagon. So then net amplitude will be like this. Now you can see that this thing here will be root 3 by 2a naught. So this whole thing from here to here will become root 3a naught. So that's our net amplitude. And this here will become our phase angle. Yes, very good, Samar. That's correct. Okay, people. So hope this particular example is clear to all of you. Okay. You can also do this trigonometrically by expanding this term. You can take omega t minus kx as alpha and just try expanding this whole term. But it's going to be much easier by this phasor diagram method, which I told you. You can do something like this over here. You can write this as a naught sine alpha plus 60 plus sine alpha plus 120, where alpha is omega t minus kx. Okay. And then you can take these two terms together using the sine A plus sine B formula and all that. But as I said, it will be easier to just work it out this way. Anyhow, now let's move on. So next thing we discussed in superposition of waves was standing or stationary waves. We saw that waves of equal amplitude and frequency, but traveling in opposite directions, on a stretched string, superimpose to result in a stationary wave or a standing wave pattern. So that on a string, if we have one wave coming from some source like this and another wave coming from some source like this. So the example that we took was like this, that if y1 is a sine omega t minus kx and y2 was a sine omega t minus kx, sorry, plus kx plus some phase constant, but where that phase constant is of the type 2 and pi. That particular special case we had seen in the last lecture. So that being the case, what we had seen is that the superposition of these two results in this kind of a, so we can think of this like a term like this. So all medium particles are in SHM with frequency equal to omega by 2 pi. Okay, and position dependent amplitude, which equals to this term. So depending on the position of a given particle, cos kx mod can be between anything between 0 and 1. So the amplitude can be anything between 0 and 2a. And we also saw that this wave pattern is not the equation of a traveling wave. So it does not represent a traveling wave. In fact, by looking at the snapshot pictures at various different times, we saw that it's what we call a stationary wave. Okay, so we saw here that the amplitude can be anything between 0 and 2A. So when we saw the snapshot pictures at t equal to 0, for example, we saw it's 0. At t equal to, for example, capital T by 12. Okay. This sine omega t term becomes pi by 6, so half. So this becomes a cos omega t. Okay. Then at y equal to t by 8, for example, this sine omega t becomes omega t by 8 is pi by 4. Okay. So it becomes 1 by root 2. So this becomes root 2a cos omega t. Then at t equal to t by 4, for example, this becomes 2a cos omega t. Then at t equal to, let's say, 3t by 4, this again becomes root 2a cos omega t. So cos kx. Writing all of these wrong, it should be kx. Then at y equal to so this is should be 3t by 8. T by 2. This again becomes 0. So on and so forth. Okay. Yeah, so now we have to define the nodes and antinodes. I know we had started with this in the last lecture. Okay. So if we look at these snapshots at various different times, so what we'll notice is that, for example, at 1/12 of the time period, the shape of the medium, the snapshot picture that is, it's looking like a cos wave, but with an amplitude of E. So this is at T by 12. And by the time you come to T by 8, the medium now looks, you can see the shape has not traveled. It's a stationary waveform. By the time you get to T by 4, all the particles except for those at the nodes have reached the maximum displacement. The amplitude of this cos graph has become 2a. Okay, then it comes back to this shape at 3t by 8. Okay, then it comes back to 0 at t by 2. Then it also goes to minus of this kind of term. And finally, so this is how the shape is progressing with respect to time. So you can see that these points, these ones, they are located at x equal to lambda by 4, 3 lambda by 4, 5 lambda by 4, 7 lambda by 4, and so on and so forth. Okay, because k into lambda by 4 is pi by 2. And cos pi by 2 is 0. Similarly, k into any odd multiple of lambda by 4 becomes an odd multiple of pi by 2. So it becomes cos inverse of 0. So these are the points where the amplitudes, so at x equal to any odd multiple of lambda by 4 here, the amplitude becomes 0. So these are called nodes. These points we label as n. We can see the consecutive distance between two nodes is lambda by 2. Similarly, if you look at these points, x equal to 0, x equal to lambda by 2, x equal to lambda, x equal to 3 lambda by 2, and so on and so forth. So multiples of lambda by 2, kx will be 0, pi, 2 pi, general n pi. So cos kx will be 1 minus 1 plus 1 and so on and so forth. So amplitude will be equal to 2a. So these are called antinodes. They are the positions where the amplitude is maximum. Okay. And they are also at consecutive antinodes are at lambda by 2. So there are alternate nodes, antinodes like this. So the standing wave has alternate nodes where the amplitude equals to 0 and antinodes where the amplitude is maximum. Such that node to antinode, the distance is lambda by 4, and node to node is lambda by 2, or antinode to antinode, The distance is again lambda by 2. Okay. So this is the important information to remember about the shape of a standing wave pattern. Especially this last part, the distance between consecutive nodes and antinodes. Also, you should understand this whole process of drawing the snapshot pictures. Okay, that's why I've done a recap of this from last lecture. Now we'll look at another example. So in our next example, we have the superposition of waves with this. Okay. So here okay, so try this out, people will discuss. So it's a slight variation of the standard derivation because you can see the phase difference is 2 pi by 3 and not 2 and pi. Okay, people. So let's start with the superposition. So pi by 3. Okay. So at any given point, the net displacement we can write as okay. So you can write this as E sine alpha plus sine beta, where alpha is omega t minus kx and beta is omega t plus kx plus 2 pi by 3. This is so this will become 2a sine omega t plus pi by 3 cos kx minus pi by 3 we can write plus pi by 2. So the standing wave equation now is like this. This is like your amplitude term and this is your SHM term. Now in all of this, we also have to find out the terms. So omega was given to us as, I think it was for 40 pi, right? Radians per second. Okay. The frequency is 20 hertz and the wave speed is 100 meters per second. So wavelength, which is V by F, is 5 meters. So K is accordingly 2 pi by 5 or 0.45 radians per meter. So now you can see from this that the amplitude at any point is equal to mod of 2a cos kx plus pi by 3. Therefore, nodes are located at the position where kx plus pi by 3 is equal to pi by 2, 3 pi by 2, 5 pi by 2, any odd multiple of pi by 2. Okay. So accordingly,
through 5 by 2 plus 5 by 12.
Sorry, come again, beta.
So it will be 5 by 2 plus 5 by 12.
Yes, I'll check it out. Yeah. 5 by 2 plus
5 by 2 plus 5 by 12. The x is equal to 5 by 12 plus 5 by 2
see,
plus 5 by 2.
this term kx plus pi by 3, na, this whole term has to be pi by 2 or 3 pi by 2 or any of these terms. Okay. So, for example, if you take 2 pi by 5 into x plus pi by 3 is equal to pi by 2. So this gives you 2 pi by 5x is pi by 2 minus pi by 3. So that is pi by 6. Okay. Now similarly, if you take 2 pi by 5x plus pi by 3 as the general term 2n plus 1 pi by 2. So that you can write as n pi plus pi by 2. Okay. So your kx term is becoming n pi plus pi by 6. Okay. So 2 pi by 5 into x is becoming n pi plus pi by 6. So x should in general become how much? 5n by 2 plus 5 by 12.
We will have 5 n by 2.
Yeah, the 5 has to be. This is what you were saying, no? So you can see that the gap between these two is 5 by 2. The gap between this one and this one. So the gap between consecutive nodes. And you can also see that antinodes are the positions where kx plus pi by 3 should be equal to 0 pi 2 pi general n pi. So here I won't take 0 because we'll take x from 0 onwards. So x should not become negative, but the first one so x will come out to be Yeah, from each of the positions of the nodes, add lambda by 4. So add basically 5 by 4 to each of these. So the idea is if you are drawing the snapshot pictures, you can also understand the medium will look like this. So if you think of a cos theta plus pi by 3 graph, how that looks like. So this is what if you draw a series of snapshots at various different times, look like this. So these are your nodes. So your first node was located at 5 by 12. So these are your nodes, whereas these are your antinodes.
Okay.
Because at lambda by 4, you can see cos k lambda by 4 plus pi by 3. That's not equal to plus minus 1. No? Understood? No? There is this term, this pi by 3 term. So that makes all the difference. Okay. So at x equal to lambda by 4, for example, the amplitude so that is minus root 3 by 2. So the amplitude at this point is a root 3. You understanding? So that is why this point is neither node nor antinode. Some in between point. Because you'll see that lambda by 4 is the point somewhere here. It's neither on a node nor on an antinode. So this point is clear, Jagannath. That completes this part. Now the third part, we wanted to calculate the amplitude at specific points. Okay. So now that's just a formula based thing. Just you got the equation of the standing wave, and from that the equation specifically of the amplitude. So you can use this equation to work out how much the amplitude is at each of these positions. Just put x equal to 0, x equal to 2, and so on and so forth. And k, you know, is 2 pi by 5 in value. Okay. So do one thing here. Instead of taking this as 2, which will make the calculation a little difficult, take this as 2.5. The calculation will be easier. Because you have a 5 in the denominator. Yeah, so the amplitude will be A. You have to take the mod, remember. So you can see that at x equal to 0, the amplitude becomes mod of 2a cos pi by 3. So cos 60 is half, so that becomes A. Then at x equal to 5 by 2 or 2.5, this becomes mod of 2a cos kx. Now this term kx will become 2 pi by 5 into 5 by 2 plus pi by 3. This will again become A. Okay. Whereas the amplitude at the point x equal to 5 will become 2a cos so again it will become A. Okay, so all these 3 points have amplitude A. But for example, if you took a point like this, x equal to 3.75 meters. Okay. So at this point, kx plus pi by 3, this term would have become so the term cos kx plus pi by 3 would have become minus root 3 by 2. So the amplitude become root 3. Okay. So this is how you can see that the amplitude is position dependent. At different points, the amplitude has different values. Okay, so I haven't done the full calculation of the antinodes positions. I've just written how you can do the calculation. So this term, okay, cos kx plus pi by 3 should be 0. So that means kx plus pi by 3 should be n pi in general. So if you substitute, solve that for x, you'll get these values. Okay, now we come to the final part of standing waves. And that is to understand standing waves created from a different situation. Standing waves formed from the vibrations of a string between two rigid boundaries. Vibrating in resonant modes. This situation we'll understand. So if we have a string that is stretched out such that it is secured between two rigid boundary points. So let's say A and B are two rigid boundary points, and this is a thread at a tension T and of linear mass density mu and of length L. So A and B, the endpoints of the string are rigid boundary points because they are rigidly attached. So they have zero transverse displacement. They cannot have any transverse displacement. So that's why they are called rigid boundary points. Okay. So now, given some vibrational energy, the resonant modes in which this string can vibrate are the following. It can either vibrate like this, such that so resonant modes, or these are also called natural harmonic modes of vibration for these strings. So these can either be like this, where these 2 points are nodes and the midpoint is an antinode. So the length of the string L becomes the distance between two consecutive nodes. Okay. So this is called the fundamental mode. So in this case, lambda becomes 2L So the frequency of vibration becomes 1 by lambda to square root t by mu. So in this case, this becomes 1 by 2l square root t by mu. So this is the formula for what is called the fundamental frequency of vibration, or you can say it is the frequency of the fundamental mode of its vibrations. So typically you can achieve this fundamental mode of vibration if you plug the string right at the midpoint. So you have given maximum displacement at the midpoint and released it from that kind of position. So it will go into this natural mode of vibration where the midpoint is an antinode and the end 2 points are nodes. Okay. Now, likewise, this can also vibrate in a mode where this is what happens, that this is called the first overtone mode. So it can also vibrate in such a way that the two endpoints, instead of being consecutive nodes, the midpoint is also a node. So the string could be vibrating like this, such that the points which are at quarter of the length distance from the endpoints, they are the antinodes. So in this case, you can see that the length L becomes equal to lambda, because the distance between consecutive nodes is lambda by 2. These are the antinodes, lambda by 4 lengths. Okay. So for the first overtone mode, lambda is equal to L. That means the frequency of the first overtone, which we label as F1, becomes 1 by L square root T by mu. So we also have this formula that the frequency of the first overtone is 2 times the fundamental. And like that, we can see that there's a whole series of harmonic overtones. The second overtone, the string will look like this. So there are two nodes in between now. Apart from the endpoints, there are two other nodes. So there are 4 nodes in all and 3 antinodes. So this time this length L becomes equal to 3 half wavelengths. So for the second overtone, L is equal to 3 lambda by 2, or lambda is equal to 2L by 3. So the frequency of the second overtone becomes 3 by 2L square root T by V, or the frequency becomes 3 times the fundamental. So this is called the second overtone frequency. This is the first overtone frequency. And like that, the nth overtone mode, in that what happens is that the length becomes like this. So lambda by 2. So the frequency of the nth overtone becomes n plus 1 by 2L square root T by mu. So it becomes n plus 1 times the fundamental frequency. So this is the nth overtone frequency. So this is what we call the harmonic series, natural harmonic series of frequencies. The fundamental is given by this formula, where it depends on the physical properties, the length, the tension, and the linear mass density. The first overtone is 2 times the fundamental, the second overtone is 3 times the fundamental, and like that the nth overtone is n plus 1 times the fundamental. So these are the natural frequencies at which such a string can vibrate. And the sound that a string like this will produce when it is plucked and it goes into its modes of vibration, the pitch of the sound, what we call the pitch in musical terms, that is called, that is as a result of this harmonic series. Okay. So with this, we complete the first chapter of wave mechanics, which is transverse waves. So you can please go ahead and complete the H.C. Verma exercise on the same. In this chapter, H.C. Verma exercise will be more than enough to prepare you for the JEE exam. You can do the module questions as additional practice over time. Okay, but first and foremost, look to complete the H.C. Verma exercise, and then you will be well prepared, especially to move on to the next chapter, which will be sound. Okay, so that's it for today's session, people. Wish you all the best. The name of the chapter is Vibrations on a String. Okay, it's the chapter before the chapter called Sound. Yes, Priyank, I have shared the recording of the last two lectures and the notes on the group, but I did it early today morning, so you can just check. Okay, people, so have a nice day. Wish you all the best. That's it for today.
Bye, sir. Thank
Bye,
you.
sir. Thank you.
Thank you, sir.
Thank you, sir. Bye, sir.
Thank you, sir. Bye.
Bye, people. Bye.